Hi, can you hear me? Hi, can you hear me?
Yes.
Yes, sir.
Okay. Okay, so as I mentioned on the group that I plan to discuss the RMO paper today, and as usual, don't want to discuss just the paper, the questions, but what should we do after that? That having solved these questions or attempted these questions, what are the next steps that we should do? Can we generalize some ideas from the paper, or what are the things to learn about the questions? So and based on that we have to plan the next steps, like what are we planning to cover in the next few weeks. And I'll have to split my attention between, so some of you who have already appeared for RMO and we have scored well, so you may be planning to continue for INMO preparation, whereas for others we have to focus on the next year's Olympiad cycle. So there are kind of two different tracks that we need to pursue, so I will need to plan how to organize our time for both groups of students. Okay, but yeah, to begin with, I hope everybody got a chance to attempt the paper so that we can jump into the discussion right away. So, for question one, can you raise your hand? Those who are able to solve question one. Okay. So, I mean, both who are able to solve in the exam, that is fine, or even afterwards when you tried it at home, or those who did not attempt RMO officially, but you tried the paper at home, even you can give it a try and see what you get. So actually I feel question one is very similar to one INMO problem, right? We had discussed that, I think INMO 2004 or 2005 question. I think it was almost the same setup, right? We had some equation like some a square plus b square, some was given, right? I think there are five terms there, I don't remember, and we have to consider all the possible solutions of this, and I think we have to find the GCD of the product, right? So I think the ABCDEF, we have to find the GCD of all such ABCDEF. So in a way this is the same question which we are doing now. So now the question is, instead of six terms we have only four terms, right? Yeah, but otherwise the question is quite similar actually. So, I mean, for those who could not get this problem, I want to understand it. What was the thought process? Where did you get stuck? Because, yeah, I mean, having solved a very similar question before, the same idea should occur to all of us actually. I mean, we have to find we want actually, here we want to find the maximum value of some integer such that m divides the product. So yeah, in a way, it's the same as the GCD. It's not very different. It is slightly different in the sense that no, actually, it can be kind of similar. Just the restatement of GCD only. So as what we have done in that original INMO problem, you can go and check. I think it was in INMO 2004. So the same idea can be used here also, right? So first let us try to find the smallest possible solution of this equation. So that you can just do some substitution and check. Like as usual, we'll start with all ones, which does not work. And then after some trial and error, you will see that the solution 1, 2, 2, 3 does work. So here the product is 12, right? And so what is guaranteed is that whatever is this m that you're looking for, right? So m will be at least 12, maybe even larger than 12. Okay. So because m divides this ABCD. Oh no, sorry. Rather, I will say m cannot be more than 12 because here the product is this. So therefore, m has to divide 12. So now we have to find out, can m be smaller than 12 or it is forced to be 12 always. So there, in other words, I mean, at this point, it is safe to claim that very likely that 12 is the right answer. So now with some confidence, we can claim that we expect that 12 always divides the product ABCD for every possible solution of that equation. And so that if you break down what that implies, we have to basically prove that 4 divides ABCD and 3 divides ABCD, right? And so if we solve each of them separately and combine them, we will get this answer. And I think that is just modulo 4 and modulo 3 logic will give us that. So for example, for 3 divides ABCD, again, we know that any perfect square is congruent to 0 or 1 modulo 3, right? So therefore, I mean, the only possibility is if all of them are not divisible by 3, right? So if all ABCD are not divisible by 3, then it leads to direct contradiction, because then what we'll have is the LHS, which is simply a square plus b square plus c square, will be 1 plus 1 plus 1, I mean congruent to 1 mod 3. And RHS will be just congruent to 1. So yeah, that cannot happen. So therefore, what this forces is that therefore at least one of ABCD is divisible by 3. So 3 divides at least one of ABCD. And therefore the 3 has to divide the product. So this was the first part. And the second part is also done in a much similar way. So to prove that 4 divides ABCD, again we can break it down to 2 levels. So first part is just showing that 2 divides ABCD. So we cannot have all of them as odd. So what will happen if all of them are odd? Can somebody tell?
Then we use mod 4.
Yes, correct. So if all of them are odd, then if just going by the parity will not give us anything, because there we are getting LHS is odd and RHS is also odd. So modulo 2 will not work. But again, you have to use the fact that if x is odd, right, then we know that the x square is congruent to 1 modulo 4. And so therefore, if all of them are odd, then this again LHS will become 3 mod 4 and RHS will become 1 mod 4. So which is a contradiction. So therefore, we can say that this cannot happen, that all of them are odd. So therefore, at least one of them is even. And now there again, you can make cases that so once having proved that 2 divides ABCD, now you have to prove that 4 divides ABCD. Or in other words, there are at least 2 copies of 2 somewhere. So if possible, again, like case 1, only one. So on the LHS, the ABC are symmetric, right? So any one of them, if we assume is even, by rotation, the others can be also achieved. So we can assume that let A is even and all others are odd. So this is case 1. And case 2, where you assume that the D is the even one. So case 2, you assume ABC are odd and E is even. Oh, sorry, D is even. And in both cases, you will get a contradiction, because basically, again, going by mod 4 logic, you will see there is some issue. So yeah, I mean, as such, if you ask me, this was very straightforward problem that it is very easy to break it down systematically and predict like what are the next steps. Some problems can be tricky where it is difficult to see what is the next step, but here it is, the progressor is quite natural, that the first the equation is given, that we try to find the smallest possible solution. From that, we make a guess that maybe 12 is the answer. Then to prove that guess, we break the problem down into two parts. That we have to show that 4 and 3, both of them divide to the product ABCD, no matter which solution we are talking about for the original equation. And then it is just modulo 3 and modulo 4 logic applied one after the other to finish the problem. So I mean, I think this is a good example of an RMO question. Maybe, I mean, in if you compare to other questions, this is on the simpler side probably. But still, it is fine to start with. Like typically, I mean, not necessary, but questions can go in increasing difficulty. So then this can be the starting point for that. But as usual, I mean, having solved this question, is it giving you ideas for other questions? Like, in fact, we already seen two questions of a similar type, right? Here we are talking about a square plus b square plus c square is equal to d square. And previously in Mo, I think the question we had done was this. So now the natural progression is, can we generalize this to n terms? So can you try to answer the question that consider the equation? So let n be a natural number. Consider the equation a1 square plus a2 square plus an square is equal to sum b square. Okay, where all a and b are integers, let's say, or we can take positive number, doesn't matter. So then find the largest integer m such that m will always divide the product. So you can try to solve this question as a generalization of the given question. And then we have to see that whether our current solution approach does that generalize well, or we have to take a different approach. So to begin with, I mean, maybe I'll just give a few minutes to think right now that how will you start to approach this question based on what we have done so far.
The mod 3.
Okay. No, but I mean, the first step for us was to find one smallest possible solution, right? Because that gives us the candidate for capital M. We have to first find what is that candidate. But see, this is the most important thing. Once you see a pattern, don't leave it halfway. I mean, honestly, even I would not have predicted that such a similar question to a previous INMO problem would occur in RMO, but it happens sometimes. So, the same thing repeats sometimes, even if the same problem will not. So, you have to be prepared to deal with other questions of the same idea. And so, important for that is take the time to analyze the pattern to the fullest extent, like as much as possible. Try to find more properties and see. So, anybody who was able to find the smallest possible solution? Yes, Mihir.
No, sir, I raised my hand as well.
And for the serious, okay. But I mean, just thinking about it aloud, like what will the first step for us? I mean, we want to find the smallest possible solution. So we have to start with all ones, right? So I mean, the first attempt like that we can do is let us set all of them as one. So if I write A1, A2, AN, if I set all of them as one, I mean, it will be very lucky because we don't know anything about capital N or a small n, right? If n is a perfect square, then this sum which is equal to 1 is equal to n will be equal to p square. So if n is a perfect square, then this itself will be a solution. But we don't know that for sure. So in general, how will you try to find out that smallest solution? So if all of them cannot be 1, maybe like what we'll try to set is let n minus 1 of them be 1 and let us keep one of them variable. So let us keep first as a1 and set all of the rest of them to 1. So therefore the equation we are getting is a1 square plus n minus 1 is equal to b square. So can we find a solution for this? So suppose we keep n minus 1 to one side. So this will be p square minus, and I will not keep writing a1. I'll just write a over there. Okay, so let a be the same as a1 because we don't need the subscript anymore. So n minus 1 is equal to p square minus a square. So will this have a solution? Or in what conditions will this have or will not have a solution?
Sir, I think n has to be even for that.
N has to be even. Okay, so that n minus 1 is odd.
Yeah.
Okay,
So like we factorize b minus a and b plus a.
yes.
Then if we consider b minus a is equal to 1 and b plus a is equal to n minus 1, then we
Hmm.
get b is equal to n by 2. So n has to be even.
Right. Okay. So I mean, one way to factorize this is of course n minus 1. Like the maybe b minus 1 is equal to a and b plus a is a plus 1. And so therefore, if in that situation, what we get is p is equal to n by 2, right? And yeah, correct. And so for b equal to n by 2 to be an integer, this requires that n is even. But this is only one factorization, right? Somebody can come with a different factorization. So actually there are two cases. So case one, let n be even. In that case, what you're saying will work out. So then you'll get n minus 1 is equal to so here we're assuming that this is 1 and this is n minus 1. And so therefore we get b is equal to n by 2. And what is the value of a?
So n minus 2 by 2.
N minus 2. Yeah, okay. But in the other case, suppose b is odd, sorry, n is odd. Let us say n is of the form 2k plus 1. So then the original equation becomes 2k is equal to, so n minus 1 which is 2k is equal to b minus a plus a. So now what will happen? And actually, if you observe, right, all the examples that were done in the questions, always we are having 3 or 5, like odd number of terms. So actually, n equal to odd is the more prominent case, at least in the question we have seen so far. So now, can we factorize this as again 2 and k?
Yes.
Yeah. But then again, what you'll see is that, so therefore b is equal to k plus 2 by 2, and this will be an integer only if k is even. So actually, I was expecting that all of us to know one property, that like just taking a detour for a moment. Uh, Actually, if you consider the equation x square minus y square is equal to k. Okay, let not use the letter k. M. Okay. So where x, y, m are all integers. So what are the necessary and sufficient conditions for this to have a solution for x and y? So where let m be fixed. Okay. So this is equation only in x and y. So under what circumstances will this have a solution and will not have a solution? So obviously the idea is we want to factorize this, and then therefore uh, do you observe anything about the two terms on the left hand side, x minus y and x plus y? So if you observe, they are both have to be of the same parity, right? Because the difference between them is 2y, right? So either they have to be both odd or both even. We cannot have that one of them is even and another is odd. This cannot happen, right? And so if this is the case, what is the implication for m? If they are both odd, which means the m is odd. And if they are both even, then m is not only even, but m is of the type 4k. But if one is even and one is odd, then m is of the type 4k plus 2. So basically the conclusion is that this equation has a solution if and only if m is not common to 2 mod 4. Okay. In other words, if the RHS is such that only one copy of 2 is there in its prime factorization, then it is not possible to factorize it in this way. But if it has 0 copies or more than 2 copies, then it is able to factorize. Okay. So I mean, maybe just keep this in mind as a side note, that whenever you see an equation of this type, you can look at the RHS and conclude that it cannot be of the type 4k plus 2. Okay. So applying the same thing in this question also, we could directly conclude at this point itself that when we wrote when we said n is odd, so when we say that n minus 1 is even, so we can directly say that n minus 1 is not of the type 4k plus 2. Therefore, n minus 1 has to be of the type 4k. Okay. So basically, in either situation, we can try to get one equation or get one solution. So therefore, actually, we have to make, I guess, 3 cases. Case 1, that n is even. Case 2, n is odd. And case 3, or rather, I'll say n is odd of the type 4k plus 1. Because if n is of the type 4k plus 1, then n minus 1 will be of the type 4k. And so therefore, we will get a valid solution. But the case 3 is n is odd of the type 4k plus 3. So if n is of the type 4k plus 3, then n minus 1 is of the type 4k plus 2, right? And that same thing, b square minus a square. And therefore, no such solution will exist. So only in case 3, we will not find a solution where all of them are 1. Okay. So what is the implication of this? If you go back to the original equation, right, you are saying a1 square plus a2 square plus an square is equal to b square. What we are saying is that if I set all of them to 1, right, all of them to 1 except the first term, then this will give me a valid solution only if n is uh, n is not 3 mod 4. So if n is 3 mod 4, then I need to go one level higher. I cannot have all of them once. So if n is 3 mod 4, then what I have to do is I will have to set one more of them to be non-1. So maybe what I can do is I'll set n minus 2 ones. The last one is a1, and the second last term I can set it to 2, for example. Okay. And so then what will I get? A1 square plus 4 plus all of this n minus 2 is equal to b square. And then you can try to analyze this further. Okay. But if you observe, actually the question, the RMO question we did right now falls into this category because n is common to 3 mod 4, right? The equation that is given to us that has 3 terms. So n is equal to 3. And you see that is the reason why when we did the trial and error manually, I mean, one x type equation solution did not work and they will never work because of that 4k plus 2 argument. So that is why the smallest that we have to try is more. We cannot have two ones. We can have one single term as one and others have to be greater than one. So that is why this solution works out. Okay. But anyway, I will not analyze this complete question, but that is how you're supposed to start thinking that. So now the next step for us is that in each case, we found that smallest possible candidate for capital M. Then we have to go ahead and analyze that is that smallest candidate always going to divide that product or only in some special cases. So that is how you can continue to analyze the problem. Okay, but anyway, I mean, just wanted to share some ideas because you never know. Maybe the next time you attempt a paper, a question of similar kind, but different twist can be occurred. So you have to be prepared for that. Okay, then what about question 2? Anybody who solved this question? Okay. Yes, just a minute, let me draw the diagram first. Okay, so what is given is the semicircle with diameter AB and some points C and D on the on that semicircle, and such that the length CD is given to be fixed. And then you take a point E such that the base angles are equal. Okay, and then I think we are supposed to show that. Yes, so you can continue.
Sir, we reflect C about AB, so it will be line of circle as the AB's diameter.
Yes, correct. So basically, if we extend this line or take the reflection, they both are going to meet at the same point. So let me call it C dash. Okay.
So we if we have any chord CD, then we will reflect C about C dash and join C dash D, and E will be that our point which is equally inclined.
Yes, correct.
Yes, sir. So now if we consider O as a center, then angle COD is equal to 2 alpha.
Okay.
Yeah, then angle C dash D is equal to a alpha.
Angle C dash D will be equal to alpha, correct?
Then angle AEC dash is equal to 90 minus alpha, which is equal to CA and DEP.
So angle C dash EA will be 90 minus alpha, and that is also equal to angle CEA, correct? And so therefore we can basically know these two angles, right? These are both 90 minus alpha.
Yes.
So this whole angle is 180 minus 2 alpha, right?
Oh, yes, sir. So angle CED is equal to 12.
Correct.
And
Angle C is 2 alpha.
so that always pass through O center.
Correct. So basically, angle COD and CED are equal, right? Because given this was that we had assumed to be 2 alpha. So what we are getting is these two angles are equal. Therefore, CEOD are consecutive.
Like as a CD is constant length, then 2 alpha is constant length. So we prove
That's
both.
correct. Yeah. So basically, both parts of the question are done in one go only. Because what we are able to show is that first that circle CED, right? Circle CED passes through O always. And
Also,
angle,
sir, I have one more method. Like I
yes.
will.
Yeah, one minute. So I hope everybody has followed this method. So the main idea was reflecting C in the line AB to get this point C dash, right? That was the main idea over here. Yes, go ahead. You want to make a new diagram or the same diagram?
Like new diagram, I think, because we have to extend. Like we have to extend AC and BD.
Okay, let us extend AC and ED.
Yes, sir. Let me at point F. Uh,
Oh, let them meet at point F. Okay.
yes, sir. So now, so BC and AD are altitudes of
Yes.
triangle. So if we like mark the intersection point as H, then
Yes.
extend FH to meet
Yes.
AB.
Yes.
E. We call it that E, and by like cyclic coordinator, we can show that it's equally inclined to
Yes.
AB.
Right. So this is a well-known fact that in the orthic configuration, the altitude, I mean, these are equal angles. These as well as these angles are equal.
Yes, sir. So
Yes.
now, if we consider center O,
Yes.
then by nine, it also passed to 9 point circle.
Yes. Correct. Yeah. So because O is the midpoint of AB, so basically circle CDE is the 9-point circle of triangle ABF, right? So therefore CDE passes through O. Yeah. Yeah, both of them are very good proofs. And in fact, if you again, this was similar to a question which I had done, I think during the RMO training camp in Pratishthan. We had a similar question, right? Where we had to consider the this like I don't know if you
Yes,
remember.
sir, that I am shortlist.
Yeah, I am shortlist. There are some questions, right? I think there was some 2 points here, and we had to somehow we had constructed this point, and we have to show that these angles are equal. And so again, there we had realized that this diagram is very similar to the standard configuration. And so there, I think we had completed this, and we had to show that that altitude also goes to the same point, something like that. So in a way, it is thematically it is a very similar problem actually. Yeah. Yeah. But do you see that all of us have done 9-point circle or the configuration to a great extent, but spotting these things in the paper or in the exam, that is where it really shows how good your revision is. So like again observing that these base angles are equal and that these are 90 degrees. So see why these 90 degrees should occur to your mind, because it's a semicircle that you have to make the full use of the information given to you. So, I mean, all the sort of building blocks were there. We just had to, observe them and put it together. Okay. So, yeah, it was a very good question. I think that at the RMO level, it really forces you to think about basic ideas. Any other approach for anybody? Okay. So, if not, then again, as usual, we should start to think about what was so special about this question, that why the solution, you know, works in this case? Like, what are the properties we are using in this question? Can we generalize it in some way? So even I have not tried this so far, but I'm just thinking aloud that what, instead of like here AB was taken to be the diameter, could it be uh, any chord in the circle? So I'm just exploring on here. I don't know if we are going to get anything useful. But what I'm suggesting is let AB be any chord and let CD be again a fixed chord. So we will not change the length of CD, right? So CD is a chord of fixed length which is free to move in the diagram, but its length will not change. And now if I construct again same as before a point E such that these angles are equal, then can we say anything about this point E as CD varies? Is there anything that can be said? So that is something we have to think about. Because I mean, just to see what part of the original solution still works. If I join it to the center, still this angle is fixed. We can call it 2 alpha. But now, I mean, the construction which Ohm gave, right? Reflection of C in the line AB. Uh, I mean, that will still give me this point. But now that point is no longer on the circle. So I cannot relate this to alpha and I cannot call this alpha anymore. So therefore, there is something is different this time. And I mean, I'm not expecting to get the same property also. Maybe the property is different, but certainly that I feel that there might be some property about this diagram that we can explore and try to locate. Okay, we'll just think for a few minutes that if anything interesting is emerging from this diagram. Okay, I don't know. I'm not able to find anything useful so far, but we continue to think about it later on. And if anything interesting emerges, anybody of us can post on the WhatsApp group. But giving this attempt is very important. That finding out what more properties we can discover about related configurations. Okay, so make sure to do that for all the questions. Okay, so this was question two. By the way, I think there is a coordinate geometry solution also. I think some students must have done it, but anyway, I will not cover it right now. I think with the right choice of reference frame and coordinate system, I think you can do it that way also. Okay, then question three. Anybody who has solved question three? Yes, Janvi.
We can get bounds on M and N. We first know that M and N are perfect squares.
Yes, correct. Okay, go ahead.
We can assume M to be 10 raised to k ak plus 10 raised to k minus 1 ak minus 1 and
Okay.
so
Okay.
all ai's are less than or equal to 9.
Yeah, correct. They are all the digits of the yeah.
So then we can find a bound on k. We
Okay.
get that k is less than or equal to 3. Sorry, k is less than or equal to 2.
K is less than or equal to 2. Okay, interesting. How do you reach that exactly?
Uh, First, we can find sum of digits of m.
Okay. So sum of digits of m. So sum of digits of m is ak plus ak minus 1 plus a1 plus a0. Okay.
Which is equal to n square.
Which
M
is
is
equal to, yeah, correct.
no,
No.
the
Square
square
of
of this
this
is
is
equal
n.
to
Yeah,
n.
correct. So n is square of this. Okay.
And the largest possible value of ak plus ak minus 1 plus dot plus a
Correct.
naught is 9 times k plus 1.
Yes, 9k plus 1. Correct.
And since n is greater than m,
Yes.
so we can write m as m is less than 81 k plus 1 square.
Yes. Correct. And can we find a lower bound on m to equate this to? So for example, I mean, m has to be at least as large as the first digit, right? So 10 raised to k times ak. Assuming even if all the other digits are zero, still the very first digit has to be there. So like this is the bare minimum that has to be satisfied, right? And now here, if I mean, you can just substitute a few values, but even like just looking at this, I think everybody gets a feeling, right? See, left hand side is 10 raised to k, that is exponential. Like as k increases, the left hand side will multiply by 10 every time, where RHS has just k plus 1 square. So very soon the LHS will be much larger than the RHS and we'll get a contradiction. So we just have to find that point, right? Where the LHS will exceed the RHS. So for example, like if you set, I think k is equal to 5. So if k is 5 or any term greater than 5, then clearly this term, like if I call this term as x and this term as y, then I'll see get x is greater than y for any value of k equal to 5 or greater than 5. So therefore, I have to try k is equal to 4, k is equal to 3. Those are the things I have to try. And even in that, like for example, for k is equal to 4, what will I get? That uh, uh, so actually, one thing which I can do Jadnavi, what we did is that we directly said that this whole sum has to be less than equal to 9k plus 1. But if we are assuming that the leading digit is ak, then let us not force that to be 9 also. So actually, we can get a even more strict bound by saying that this sum is actually less than equal to. So let ak remain as it is and let everything else become 9. Okay. So do you see that this will be an even stricter bound compared to this one? Okay. So therefore, I mean, what I'm suggesting is that we'll get a much stricter inequality that 10 raised to k ak, which is less than equal to m, which is less than equal to n, which has to be less than equal to ak plus 9k square. Because now see ak is occurring on both sides, so I can make sub cases now that what if ak is 1, ak is 2, etc. Okay. So like basically case 1 k greater than equal to 5 has already been eliminated. So now I have to only consider case 2 where let us say k is equal to 4, and now here I can consider like what is the value of ak. So if k is equal to 4, then this is 10 raised to so actually even k raised to k equal to 4 is also going to be too large because I forgot. If k is equal to 4, then the left hand side is 10,000, whereas the right hand side will be simply k is equal to 4. So 4 9 is 36 square. So 36 square, which is 1296, which is much smaller than 10,000. So actually the case 1 eliminates k greater than equal to 4, right? So now I have to consider case k equal to 3. So if k is equal to 3, then this inequality becomes 10 raised to 3 ak or a3. Okay. And I think here we'll find that, I mean, I think no matter which value of a3 you use, you are going to get a contradiction, because at the like if I start with a3 is equal to 1, then the LHS is 1000 and RHS is 28 square, which is definitely less than 1000, and so on. So if I keep increasing a3, the LHS is going to keep increasing much faster than the RHS. Okay, so we can eliminate this case also. Okay, so then we are only left with the case where k is 2. So in other words, m is a 3-digit number or less actually. So I should say less than equal to 2. So if m is a perfect square and a 3-digit number, then like we know that there are very small number of cases to be tried, right? Basically 1 square, 2 square, 3 square. So m has to be one of these. 1 square, 2 square, 3 square, all the way up to 31 square is the largest perfect square up to 3 digits, right? So they have to be one of them. But can we do a, like we still have to try out 31 numbers, or can we do even more optimization? How can we eliminate further? Jannavi or anybody?
We can use that n is greater than m, so we can choose those values of m such that the square of the sum of the digits is greater than m.
Yes, correct. Any other way? So basically, whenever we are talking about estimation, or we have to try to reduce the number of cases, there are two approaches, right? One is bounds based estimation, or rather no, I should say bounding by estimate. I don't know what I have to say. Basically, there are two ways to restrict the number of solutions. So one is through bounds. I don't know what I want to say, but basically there are two threads. Like divisibility is the second thread, is what I'm trying to say. That one is estimation, like trying to find inequalities, and the second is through divisibility. So can you think of through divisibility how can I restrict the possibilities? Because remember, going back to what is given, s of m square is n,
Then we
and
can use mod 9.
yeah, exactly. We can use mod 9, right? Because we know that the sum of the digits will be congruent to the original number. So, I mean, if I put both of these things together, basically modulo 9 s of m is congruent to m, right? So f of s of m square is congruent to m. So basically I need m square congruent to n modulo 9 and n square congruent to m modulo 9. So I'm looking for those remainders which I, or if I combine these two, right? If I just substitute n from the first equation, the second into the first, and say m raised to 4 is congruent to m mod 9. And so there are only a finite number of remainders of m, which will give me this property. Like if I just list out all the remainders mod 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. I think out of them, and whether you can factorize this also to get this. I think 0, 1, 4, and 7. These are the only ones which satisfy this common ones. Okay, so these 2, 3, 5, 6,
Yes, sir.
they all get eliminated. So you see, we are able to restrict the number of trial and error on two axes. One is what we did so far previously was the inequality approach. And so that gave us one bound that m has to be less than 31, right? And now what we are saying is m also has to be congruent to 0 or 1 or 4 or 7 mod 9. So the combination of this and this is going to restrict your possibilities very quickly. So I think so only possibilities to try for M are 1 square, 4 square, 7 square, 9 square, uh, 10, 13, 16 square. Yeah, I think that's all. 28. So instead of trying 31 values, we just have to try some 12 or 12 values now, 12, 13 values. Okay, and I think the answer turns out to be, so I think both of these are true, right? 9 square and 13 square, they are both satisfying the equation. But because we are given, yeah, when m is 9 square, which is 81, we get n is also 81. And so that does not allow, because m less than n is given, so therefore we have to eliminate this solution. And so you get the only other solution is m has to be 13 square. Okay. So this question had some trial and error. I think all of us can agree that it was not directly that you get the solution in a clean way. You have to do some trial and error. But what you have to learn is how to minimize the trial and error, that how you can use both these ideas. So estimation and divisibility. And this is a common theme in many number theory questions. Like when often it is not just divisibility that is going to solve the question. You have to use some form of estimation as well. So learning to use both of them properly is an important technique for us to learn. Okay. Any other alternate solution? At least I have not seen anything different that can be done. Mostly, maybe there are some ways to do these inequalities more in a different way. But at the end, finally, you are going to estimate some bounds, and from that only you are going to get. I don't think there is any way to directly find the answer for a question like this. So, I mean, more than ever, looking at a question like this, you have to pause and think that how could this person, whoever said this question, how did they think of this idea? Why did they think of this question? Like, it's not like, you're dreaming and suddenly you get a dream that let us ask the question s of m square equal to n, s of n square equal to m. There has to be some process, right, through which somebody arrived at this possibility that we can ask this question. So if you think about it, that what can be that process, that will make you a better problem solver, because then you will, whatever logic is going through the paper setter's mind, if that is going through your mind also, right, then you will be much more in alignment that what is the ideas that are being tested here. So we are trying to test estimation, we are trying to test divisibility. So you'll naturally think of the right ideas. Okay. Instead of trying other directions, you'll quickly land on the right direction. So for that reason, it's important to just think about it, that how, if you were to create a different question. So this is your homework, that now try to create question 3.2. So that is your version of this question. What will you change in the question? How will you modify the question to make it your own question? Okay. So if you try to do that, of course, very likely the question that you will design will not be of the level of RMO, because we don't have that much experience. But making that effort is the most important thing. Okay. Okay, so that was question 3. Then coming to question 4. Anybody who has solved this? Okay. It's Nandini. 1 minute, let me just draw the diagram. Okay, A, B, C, D. And what is given are, we take the bisectors of the two segments. And I think P and R of the same side. Yes, go ahead.
Yes, sir. Let O1, O2 intersect the bisectors, perpendicular bisectors at some points x, comma y.
Okay.
And we know that quadrilateral PRSQ is a trapezium.
Yes, correct.
So we get that the midpoint of PR, if we join the midpoint of PR and QS,
Yes. So midpoints of PR, QS, and I think XY, right?
yes.
Yeah, are collinear, correct?
So we have to prove that the midpoint of XY is equal to the midpoint of O1, O2.
Yes, correct.
For that, we have to prove that O1x is equal to O2y.
Yeah, so yeah, if you prove that O1x is equal to O2y, we are done, correct.
Yeah, and then I proved one lemma. If there is one angle and four parallel lines,
Okay. What is the diagram I should draw?
you can first drop perpendiculars from O1 and O2 to L.
In the separate diagram, right?
No, in the same diagram it is okay.
Okay, okay. So L is this line. Okay. So these perpendiculars. Okay.
Yes,
And
can
should
you name
they
the points?
label the points? Yeah. Okay. What is E and F.
And also the intersection point of AB and PQ.
A, B, and P. Okay. So these points.
Yes, I proved that KE upon XO1 is equal to FL upon O2y.
Okay. K E upon X O1 is equal to FL upon O2y. Okay.
We can prove this by theorem of three parallel lines.
Yes. Okay. Yeah. That is fair. Yeah. Okay.
So we have to prove that KE is equal to FL.
Yes. Correct.
And we know that KE is equal to KC minus EC.
KE is equal to KC minus EC. Yes. Correct.
Which is equal to BC plus AB upon 2 minus AC upon 2.
Wait, let me just understand. Yeah, actually, I understand the overall approach you are making. So basically, on the line L, now we can chase the lengths, right? Because we know that K is the midpoint of AB and L is the midpoint of CD. So I think we have all the information to actually compute KE and FL in terms of the given distances, right? That is
Yes, we get it is equal to BC upon 2.
yes, correct. Yeah, so we get K is equal to BC upon 2, correct. Yeah. So we get K is equal to BC upon 2, and the same way we'll get FL is also equal to BC upon 2, right? Yeah, so therefore K and FL are equal. Okay, yeah, fair. Anybody else? Swami?
Yes, same method.
Same method. Okay.
Yeah,
Om?
yes, sir. So same, but like we prove that K is equal to FL. Then I draw perpendicular from O1, O2 to PQ and RS.
Okay.
Then they will be equal because it's a rectangle.
Yes.
And then we will extend them and then prove that the midpoint of O1, O2 will be lie on midline of that trapezoid.
Okay.
Yes.
Yeah, fine. So yeah, all of them are valid ideas, and I think the most important, the strategy which Nandini you started, that was the right one. That if you notice that PR and QS are already on two parallel lines, so basically what I have to show that O1 O2, the midpoint of O1 O2 is also on the parallel line between PR and QS, or in other words, O1 and O2 are equidistant from PQ and RS. So that was the main thing. Okay, any other approach? So there is one shortcut which I think all of you missed. To the approach is exactly the same, but I can just finish the problem in one line. if I show you one thing. Okay, and this is actually this question, there is a background to this question which I will not talk about right now maybe, but there is something very interesting about this question which may be interesting to discuss later on. Let me just draw one part of the diagram. So I will not draw both circles. Let me just draw the left circle. Okay, so this is what we have, and so the points A, B, C, and D. I don't care about D right now. And now I consider the perpendicular bisector of, right? This is the perpendicular bisector, and we have this point P and Q. So, and we care about the point O1 and its distance from the length PQ, right? This is the distance that we care about. So, again, this is a diagram which we know very well, just that we didn't recognize this diagram. Can anybody recognize this diagram? Distance of O1 from the line PQ. If I call this point M. In this triangle, what is B?
Ortho center of PQ.
Isn't B the orthocenter? Because I mean, this is a standard configuration which I think everybody should know. In a triangle, if we consider the altitude where it meets the circle again, so then we know that the orthocenter is the reflection of that point. So isn't it, if B is the orthocenter, how much is O1M going to be? If B is the orthocenter of triangle PQC, so then do we know anything about O1M?
BC by 2.
Is BC by 2. And very curiously, I mean, now in this diagram, if I add the other circle, see that the BC common to both circle was the key part, right? In the second circle, we have again the same configuration, right? There is a perpendicular bisector RS. And now in this diagram, C is the orthocenter of, so in very similar, C is the orthocenter of triangle BRS. And so therefore O2N is also BC by 2. And so therefore these two are equal, right? So I think what all of you did ultimately gave the same answer, but just that if you just observe it as the orthocenter, you can get it in less calculations. Okay. So again, the key idea for this solution was spotting that configuration. But yeah, I mean, as all of you have changed that, it is not necessary to observe this, but if you do it, it can help in some situations.
So we get B's ortho center because the reflection lie on that circle.
Yeah, because that is a unique point of the tree, because we know that that is the only point which, if reflected, it will go to the circle. So yeah, that is a sufficient justification. Okay. So yeah, I think everybody who has attempted this question would be one of these approaches also. I think again there is a coordinate geometry solution which somebody has written, but we don't have to discuss it right now. But one important thing I want to observe about this, that this is a very interesting configuration where we have perpendicular bisector of not of the chord but of a sub chord, we can say, right? AB is a sub part of another chord. And so when you take the perpendicular bisector of that, we get an orthocenter kind of configuration. Not only that, let me draw a different diagram. And I want you to, as a homework, try to analyze this diagram. And why I'm asking you to analyze that, we'll discuss in the next lecture. But there is some importance to this diagram, and that's all I will say. So consider circle with a point A on the circle, and consider circle with center A. Okay. Okay, so if I call it gamma, so gamma is a circle with center A and some radius. Radius does not matter. So the important thing is that the center of this A is itself on another circle. Okay. And now in this diagram, consider any line. Okay. Same as before. Consider a line that it meets the circle at point B and C. And now consider the perpendicular bisector of BC. Okay. And so let this point be some X and Y. Okay. And now this line will vary. So the circle, the red circle and this point, these are fixed. Okay. But this line BC will keep changing. So in fact, let me call it B1, C1. Okay. Just to indicate that this is a special position. So I can keep varying this line. Like for example, somebody could take a different line over here, B2, C2, and draw the perpendicular bisector of that. And you'll get a different X2, Y2. So as this line varies, many things remain constant. And so what all remains constant is for you to find out. Like for example, already what we observed, because this B1 will always be the orthocenter of triangle AX1, Y1, right? So do you observe that this, like if I call this length D, then this will always be D by 2. And therefore, basically the length of X1, Y1 will also be fixed always. So although this line is changing, the length of X1, Y1 will not change. So in fact, I'll get X1, Y1 is equal to X2, Y2. Okay, but this is just the starting point. There are many other things you can analyze in this diagram. And if you do all of these things, actually, you will be in a position to solve one IMO problem. But which IMO problem, I am not revealing right now. Okay. But if you want to solve that IMO problem, you have to analyze this diagram completely. Okay. So that was kind of the point of this question, that we want to motivate ideas which will help you to solve harder problems, INMO, IMO, shortlist, IMO problems. Yeah, where the same theme is going to be used there. So it will be surprising for you to know that whatever done in this RMO question, applying the same ideas, you can do a much harder problem also. Okay, so that was about question 4. Okay, question 5. Anybody who has solved it? Okay, interesting. Nobody has solved it. What about question 6? Anybody has solved question 6? Oh, interesting. So both question 5 and question 6 are difficult in that sense. So let me think. We just, instead of giving away the solution, can I motivate the solution using some smaller problems of similar kind? So maybe let us do question 6 first. Okay. So question 6 about I mean, in most cases, I think you must have, whoever tried this question, you must have run into so many cases and try and error, right? It's not straightforward to figure out that how to try this problem. But understand that before we try to solve the problem, we have to start with some observation that we are interested in isosceles right angle triangles. So triangles of this kind, right? This kind, or even they may be rotated, like they don't have to be parallel to the sides of the grid. They can be like this, they can be like this. So all of these are what we're looking for. So can we find, I mean, this is how we have to start thinking about a problem like this, that finally we are going to color 7 out of 16 points. So this ratio is very important, 7 upon 16. Okay. Any combination of points where we can find that. So let me state this general statement, that consider some Q points arranged in some formation, so that I will, this is on fill in the blank. So I will fill this blank later on. And if at least P points are colored, we can okay. So some arrangement of Q points such that out of that, if at least P points are colored, then we can guarantee an isosceles right angle triangle. Okay. So this is the statement which I'm making. Where, you know, of course, this is a very blank statement where Q, P, this arrangement, they are all fill in the blanks. But my point is this, if we can find this arrangement such that this ratio P upon Q is greater than or equal to 7/16. Okay. So in other words, there is some set of points for which if more than 7/16 of those points are colored, then I can guarantee to find the right isosceles triangle. Then what I will do, that whatever this shape is, right? If I call this shape X, I can just use that as a tiling. Like I can tile the whole diagram using that shape X. I suppose, like, I don't know what is that shape, but suppose the shape is something like this. Then what I'll do, I'll just fill the whole diagram with tiles of that shape. Okay. And so what will happen in each region of those, if that ratio P by Q is met, then I'm going to guarantee a right angle triangle. And I only want to find one right angle triangle. So it is not like every region has to cross that threshold. Even if one region crosses the threshold, I'll get a right angle triangle. But more importantly, what will happen is that suppose the total, if there is no right angle triangle, because understand the converse of this statement, that if no right angle triangle exists, then what you can guarantee is that less than P by Q of those points are colored. Okay. And so if happens that this region does not have a right angle triangle, so the total number of points colored in this region has to be less than P by Q. And same in every region. And now if I add up all of them, I will get that the entire whatever region you are considering, all of it has to be number of points colored is less than P by Q. And that will be the contradiction, because we know that at least 7 points are colored. Okay. So I'm just giving the most broad possible strategy, that if you have a question like this, how you can try to approach it. That we have to find this small part within the whole question, which can be broken and solved like this. Okay. So this is the general direction in which we would like to go. Okay. So for that, what is the most important thing? We have to find examples of points for which this ratio P by Q is as high as possible. Okay. So what do I mean by that? So for example, suppose I just take 3 points. Okay. Okay. So now can you answer me the question that out of 3 points, so if Q is 3, how much is P? That what is the minimum number of points that will need to be colored to guarantee that I will get a right angle triangle? All 3, right? Basically, if I just color 2 of these points, that will not form a right angle triangle. So if Q is 3, P is also 3, right? But suppose I have 4 points. So Q is 4. Now how much is P?
3.
Yeah, P is 3, right? So see, this ratio P by Q is 3 by 4 here, and here the ratio was 4 by 4. Oh, sorry, 3 by 3. So you see, this is a very good building block, that if you have 4 points, then out of those 4 points, I need at least 3 of them colored, or rather, if any 3 of them are colored, I'm guaranteed to find a right angle triangle. So we have to find even stronger building blocks. So what about this arrangement? Out of these, what can you say, that how many points can be colored?
Still 3? No, so it would be 4.
If you color 4 points, you will be guaranteed to find a right angle triangle, right? If you color 3 points, what will happen?
One of the diagonals can be
One of the
colored.
diagonals can be colored. So actually, this is a case where I have to consider 2 cases. That either, like, suppose I color 3 points. If let me write it properly. If 3 points are colored, then two things can happen. Either I'll get a isosceles right angle triangle is formed, or if no such triangle is formed, then it is forced that one diagonal is colored, right? I leave it as exercise for you to check that one of these has to happen. Without forming a right angle triangle, it is impossible to color a non-diagonal. Like any 3 points, if you color apart from a diagonal, you will always form a right angle triangle. Okay. So in other words, if 3 points are colored and no, like I can invert this statement, right? If 3 points are colored and no isosceles triangle is formed, then I can force that there exists some diagonal which is fully covered. Okay. And if you observe something about this diagram, right? What I was saying about tiling the diagram. So, like if I consider this as a building block, you see I can displace this whole arrangement by one level to the left, let's say. And I can consider this other set of points. Okay. Which has the same shape as the black one. So the same statement will be true for this red shape as well as the black shape. So now together for this whole shape, can you tell me how many points will I need to color? See, individually, I see that in the black region, I can color 3 points, and in the red region also I can color 3 points. So you may feel that together the whole region can take 6 points without forming any isosceles triangle. But if you think about it, that's not true, right? Because if let's say the black combination, right? If let us say I'm going to color these 3 points, then I no longer have the freedom in the red part to color any diagonal. So there is an interdependency. I cannot solve both parts independently. So can you tell me, like, what is the maximum number of points I can color in this without forming a isosceles triangle?
So 2.
No, I'm saying, so there's a total, how many points are there? 12 points, right?
Yeah, I mean 3 plus 2, 5.
Okay, 5.
No, sir, no.
Oh, by the way, sorry. But these are not 12 points because I forgot. Actually, there are some cavities here, right? We are not considering these 2 points. Sorry. So actually, there are only 10 points here. So actually, my claim is that out of these 10 points, if any 5 are colored, I will get isosceles triangle. Isosceles right angle triangle, always. So here, what I'm saying that this is a set where Q is 10 and P is 6. So the ratio is 6 upon 10, which is even smaller than the previous one we got. So this was 0.75, this is only 0.6. So you see we are getting larger and larger set for which the total fraction of the area that needs to be colored is even smaller and smaller. And ultimately, we want to reach 7 upon 16, which is actually less than half. But if we continue along this journey, we will get there. Okay. So that is the sort of motivation which I'm trying to give. Okay. So basically, what I'm trying to say is the strategy, right? The strategy for this question is find the right tiles. Okay. Then use them together to cover the whole area. So whole area means in our case it is the 4x4 grid. Okay. So there is some trial and error involved. Which is the tile you will use, how will you cover the board? But that is the main idea. So for example, let me just start with an example that how you can try to tile the board. Okay. So I'll use color or maybe shapes to denote the tile. So all those points which I have circled, that is going to form one tile. These triangles will form the second tile, and this will form the third tile. And so I'm dividing the 4x4 board into 4 tiles of 4 points each. And the key thing is that each of them is forming a square. So I can make cases. So case 1, so the middle triangle, right? This diamond shape. So the diamond tile is not used at all. Okay. Suppose there are no points colored in this diamond tile. Okay, which means that all the 7 colored points are in the outer ring. So all the 7 colored points are in the only in the outer ring. Then can we finish the problem? Because there are basically there are 3 groups of 4 tiles each, right? And there are 7 points which are colored. So can you guarantee that there will be some group out of which 3 points will be colored? Okay. Because otherwise what will happen? I have 3 groups. If each of the group has only 2 points, then 2 3s are 6. I'll only get 6 colored points. So this is just pigeonhole principle. Okay. And so whatever that group is, because that group is forming a square, right? So in other words, we are using that square arrangement first. So therefore, in any square arrangement, coloring 3 points always forms the right triangle. That is easy to check. Whenever you are forming a square, any 3 points you color, you always form a right angle triangle. And so, for example, like suppose this is the group out of which if you color any 3 squares, any 3 points, you will guarantee to form a isosceles right angle triangle. Okay. So this is the probably the easiest case to deal with, where the central region is not used at all. What if? So similarly, you have to consider other cases. So case 2, only 1 point of the central region is colored. Or actually, I will make the case that at least 1 point. Okay. So now what will happen if 1 point of the central region is colored, the outer region no longer has 7 points. It may have only 6 points which are colored. So we cannot use this argument anymore. Okay. So we have to change the tiling. We cannot use the same tiling. We have to use a different tiling. Okay. So, but again, your inspiration has to be what we did before. So, like this kind of cross pattern that we observed earlier, that has to be used in some way over here. So, like, let us say without loss of generality, consider the top left point as color. Okay. So, your diagram looks something like this. Out of this, only this point is colored, is given to us. So, we still have 6 other points which can be colored. So the question is, can we start to form these tiles so that out of each tile, a certain minimum number of points have to be colored and such that that total fraction will exceed that 7 upon 16. So for example, let me just mark here as tile 1. Okay. So number 1, they are all going to form one tile. Okay. And so if you see out of ones, uh, at most 1 point can be colored. Right? If two of these reds are colored, we are going to get a right angle triangle. Similarly, what about this tile? 2, 1, 2. I'm using this blue point cleverly as a pivot point, that any triangle which is formed using the blue point will give me these kind of pairs, right? Again, out of the two tile, at most 1 point can be colored, and I can keep going that way. Maybe like 3, 3. Again, out of 3 tile, at most 1 point can be colored. And so finally, if I add up all of these, what I would expect is that the total has to be at the most 6 points can be colored. Oh, sorry, not 6, actually 5. If I am able to do that successfully, what that will mean is that I have at most 5 points plus this one, right? The 6th point. So I can only have 6 points colored. So if whenever I color the 7th point, it is going to fall into one of these tiles, and that is going to form the isosceles right angle triangle. Okay, that is the strategy which I am trying to indicate. Okay, so I'm deliberately not giving out the whole details because I would like you to try the question first. Okay, that how we are going to break up the problem into these tiles. That is the whole thing. Like for example, one more time to mention 4, 4, 4. So see, this is a particularly valuable tile, this 4, 4, 4, because it is covering more points, but still in that only 1 point can be colored. Okay. So I'll just wait for a few minutes if you want to think before I complete the solution. Okay, so the idea which I will suggest is that we can form this tile now 5 5 5. Okay, again out of this tile, if you observe that only one point can be colored. If you color any 2 points, oh no, sorry, not that tile, the central tile. So again, out of these 3 points, at most one can be colored. Okay. So therefore, the total, if you see here, the total number of points out of all the points I have highlighted here, at most 5 points can be colored. So, but that still leaves us 2 gaps, right? These two are still the gaps which are remaining, which we are not covered. So what we can do is we can divide this problem into further cases. That so if I label these cavities as A and B, right? A and B. So like case 1.1, A and B are both non-colored. Or I mean, I have to say that neither A or nor B are colored. Okay. So if A and B are both not colored, then we have completed the argument, right? Therefore, in that case, what we are getting is that remaining 14 points at most 6 can be colored. Why 6? Because all of this set, right? Each of them can have at most one colored point and plus the one which you already colored. And that will give the contradiction because we are clearly given that 7 points are colored. So case 1 where A and B are both, neither of them is colored. Then case 2 is one of them is colored. So exactly one of A and B is colored. And by symmetry, we can, because the whole diagram is symmetric about this axis, so I can choose any one of them as colored. So without loss of generality, let us say that A is be covered. So given that A is colored, what does that change for us? Now we can change the tiling because we can take away the tiles from some places, right? Previously, like for example, this point, if you look at this point, we had kept it in the tile number 1. But at that point, we did not know whether A is colored or not. But if A is colored, then that point can never be colored. So that we can sort of strike that point out of our consideration, right? Okay. And by the way, I mean, because I'm explaining the thought process behind the solution, it is appearing very long. Finally, if you know condense it down to the solution is actually just 4 or 5 lines of proof. Okay. But now what is given is these 2 points are colored. So as a result, you will see that many other points now become invalid, that they can never be colored. So in fact, this is going to reduce the number of, so that if we are talking about that P by Q, right, this is going to reduce Q substantially, the denominator, because so many points will go away that they can never be colored. Right? Any other point I missed? Yeah. So see 1, 2, 3, 4, 5. 5 points are sort of eliminated from our consideration. So now we have to form the tiling with only the remaining points. Okay. So for example, the tiling can be same as before. Let us say 1 and 1. So one tile at most one colored point. And they can proceed this way. Continue to form tiles. 2 tile again at most 1 point colored. Okay. So do you see in this tiling, what is happening? So the total number of points that are allowed to be colored is 4, plus the 2 which we already colored here, like these 2. So therefore, total number of points which are allowed to be colored is 6. Again, a contradiction. So like that, in every case, you are going to get a contradiction. So which is the only case remaining? So we have done the case where A and B are both not colored. We did the case where exactly one of them is colored. And now we'll do the case where they are both colored, right? Okay. But I mean, assuming that you understood the idea, I think now you can work out the details. So now what is given is all these 3 points are colored. And so that is going to take away, and you see how this is a balancing act, that when you assume that more points are colored, this red crosses will increase, right? The number of points which is eliminated will increase, but at the same time, your budget of remaining colored points reduces, right? So like how many remaining points you are allowed to allocate. So we have to have less number of tiles now to cover the same region. But that is okay because now the number of points to be covered is also lesser. So like here, if you see, all of these are going to go away. So you see 1, 2, 3, 4, 5, 6, 7, 8. 8 points got eliminated. So now we are left with only 1, 2, 3, 4. Only 5 points are remaining. So that, I mean, there it should be very easy to do the tiling. So out of these 5 points, our claim is that if any 4 points are colored, this is our claim, right? There exists a isosceles right angle triangle. Okay. So I think that is a very easy thing to verify, because what is going to happen now? Again, same as before, we can do the tiling systematically if you want. So for example, this can be tile 1, at most 1 point is covered. And this can be tile 2. So in fact, what we are saying is that we are sort of running out of points. We want to color 4 points, but out of this group number 1, only 1 point can be colored, and group number 2, only 1 point can be colored. So we are actually running out of points. Like even if I color this, right? Suppose I color this. Even after that, I have 3 points remaining to be colored, and so 2 of them have to fall in the same tile, either tile 1 or tile 2. Okay, so that is how the argument can be completed. Okay, so I know, I mean, I think this is definitely a difficult problem. It is not easy to figure out, definitely in the time limit. But the building blocks are very simple if you think about it. It is all about that ratio P by Q. That what fraction of the whatever tile you are considering has to be colored in order to guarantee a isosceles right angle triangle. Okay, but actually, finally, if I condense all of this into just a few lines, let me just write those few lines. That, I mean, you'll do all of this in the rough work, but in the fair work, what will be there? Case 1, no center point is colored. Okay, in other words, the diagram looks like this. These all are gone. Then this is tile 1, tile 2, and tile 3. So this was case 1. Then case 2, at least one center point colored. And in that we consider sub cases like case 2.1, A, B, both blank. Okay. So where, I mean, that A, B that we talked about. So this is blue. A is blank and B is also blank. And so in this case, we could do this kind of tiling. I will not repeat the tiling here, but I think you understood the idea that. So that is the case 2.1. Case 2.2, exactly one color. and case 2.3, both A and B colored. Okay. So actually, just in these 4 or 5 cases, the problem is getting solved. But arriving at those cases is the difficult part, which even I think, yeah, it can be challenging to think about. Okay. So, I mean, for those who attempted RMO, like what you are supposed to write, even if let us say you were not able to solve the problem in the exam, how, what can you do to maximize your score, like to get some partial credit or things like that? So, I mean, first thing is that what are sub cases? Like, I think this case one was quite easy to figure out that no center point is colored. So, if you even if you do that sub case, you will get some marks for that. Then the lemmas that you observed at the beginning. So the first lemma about 4 points, right? Out of 4 points, out of 4 square points, at most 2 can be colored. This is an important lemma. Okay. If you solve this lemma, you will get some points for that. Then even that cross lemma, right? Out of 5 points like this, at most 2 can be colored. Sorry, at most 2 can be colored, or there exists a diagonal which is fully colored. So if you solve these kind of lemmas, you will get some partial credit for that. Okay. So I mean, there are two things which we need to clarify. That one is how you approach the problem, like what are the ideas we should try, and no matter how much you are able to make progress, what you should write to get some partial credit for your attempt. So both of these things are important. Okay. So this is one solution. And there may be some alternate approaches also, but finally you have to do some amount of casework. I don't think that is completely avoidable in a question like this. Some cases have to be solved. Okay, but keep this that P by Q strategy in mind, because the question will change. You know, maybe tomorrow you'll have a different question where we are not talking about isosceles right angle triangle, where we are talking about some other shape. But this P by Q ratio is the common denominator. That how do you minimize that P by Q ratio? That is the most important thing. Okay. Okay, so this was question 6. And so now I think only question 5 is remaining. Um, any ideas about question 5? I think Raghav solved it, right? But I think he's not there today. Okay. Yeah, but actually Raghav highlighted the main idea in on the WhatsApp group. If you have not read that, he has given one important hint. See this k minus 1 and 1, right? They look a lot like weights. That I mean, if you know how section formula looks like, right? If you imagine the section formula for like, can you construct this in a geometrical way, like this whole expression, right, which is given over here? Can you think of a way to interpret this geometrically, at least the reciprocal? Okay, so k minus 1 a raised to k plus 1. Okay, so how do you try to interpret this geometrically? So I mean, as soon as I look at an expression like this, I see that this k minus 1 and there is an implicit 1 into 1 here. So k minus 1 and 1 are the weights, and their sum is also appearing in the denominator. So this is how you should be able to imagine this question. Because if you do that, then what you can do is we can think of this as ai raised to k repeated those many times, right? It is ai raised to k plus ai raised to k plus ai raised to k repeated k minus 1 times. And now we'll try to apply AMGM. Okay, so suppose these are k minus 1 times this. So there are total k terms now, right? So this whole thing upon k is greater than or equal to their product. So that is ai raised to k raised to k minus 1. And we are going to take the kth root of that. Okay. So if you simplify this, what are you going to get? So LHS is going to become ai raised to k minus 1 times. And on the RHS, that kth root will cancel with the k inside, and you're going to get ai raised to k minus 1. Okay. And so now to convert this expression into this one, you just need to divide by a raised to k, right? To get that. So therefore, k minus 1, a raised to k plus 1. And so if I take the reciprocal again, sign will flip. Right. And so therefore, if I take the sum of this as I goes from 1 to n, right? So therefore, what I'm going to get is this whole sum is less than equal to this sum. And now this sum itself is going to be less than equal to n. Okay, that is by sigma root ai. You can apply AM RMS inequality, like for example, root of a1 plus root of a2 plus root of an whole upon n will be less than equal to square root of the square of all of this. So root of a1 square plus root of a2 square, etc. upon n, which is nothing but 1. Because this is simply a1 plus a2 plus an, and that a1 plus a2 plus an is given to be n. Okay, and the important thing is that this it is given that this is equal to n, which means that we are dealing with the equality case, and we know that equality happens if and only if all terms are equal, right? So equality if and only if all terms are equal. So therefore, a1, a2, an, they are all equal to each other, and therefore they have to be equal to 1. Okay, this is the I think yes.
Like where we use the fact that n is greater than k.
Where have we used what?
The fact that n is greater than k. It's
No,
given
we have not used that. Actually, that was not required access. K could be any integer, doesn't matter. I think that was unnecessary information.
okay.
Yeah. Okay. But actually, I should have talked about this before. Even before you start calculating, looking at this question, I think it was a very safe claim, right? That a1, an, they are all going to be equal to be 1. And the reason for that is, if that is not the case, right, then very likely there are infinitely many solutions for this. Like if clearly the information given is so much less than a number of unknowns. So whenever you have that situation where you have n unknowns, but you are given only 2 equations, so clearly there is a very odd imbalance that you cannot extract information about n unknowns out of just 2 equations. Only case that is going to happen is that this is like some special corner case, like it is an equality case or something like that. So this is like a very clear indication that we are talking about inequality, but reduced to a equality case. Okay. So although the question did not have any mention of inequality, but the setup is such that there is no choice but to apply some inequality. Okay, so that first, I think we have to start with that observation that this is an inequality problem without actually using the inequality sign. It's a paradoxical thing. Okay. Just to mention one more thing on this problem is that there is one more solution possible actually. But I myself am not able to work out the details. My conjecture is this, that as k increases, or as k goes from 1, 2, 3, 4, etc., what happens to the LHS? Okay, so what happens to this term? Okay, so I mean, this is an open question for you also. Like if I call this as a function of k, right? As k changes, the value of this expression will change. So if I try to plot that, right, what will that graph look like? And based on that, I think there can be one more solution. But I'm not still worked out the details myself. But anyway, something for you to think about that. Intuitively speaking, if you think about it, right, as k changes, right, if I go back to the original interpretation of this, like if this is a weighted sum of 2 numbers, then as k is increasing, I'm increasing the contribution of the first term relative to the second term. At the same time, I'm also increasing AI raised to k. Actually, so that is where the difficulty lies. See, if AI is greater than 1, then as k increases, the value increases. But if AI is less than 1, then as k increases, the value decreases actually. So then there is a conflicting interest there. So that is where even I'm stuck. But my hope is that to prove that as k, there is a monotonic function with respect to k. So therefore, it is enough to consider one extreme case. Okay, that is the idea which I'm trying to work out. But anyway, I mean, I've not done it completely. Okay, so that was the analysis of this question paper. I still don't know about the cutoff. Maybe we actually will start evaluating sometime next month, next week or something. So, but my estimation is that if you have done at least 3 problems, then you should be in a comfortable position. But we never know. Only after we have done the whole evaluation, we'll be able to say as such. But I think still there are some questions which were very good, that they gave a lot of insightful information that really try to test you in various ways. That are you able to think, apply configurations of different kinds? Like question 2 had 2 approaches, where out of them, one of them used that ortho center configuration. Question 4 also one of the approaches, or at least one step, you can apply the ortho center configuration if you want. Question 3 has some part of trial and error, but doing that smartly is the skill that we are testing. That are you able to apply the estimation, get the number of cases reduced to a finite things to check. So those things were checked on that. So yeah, I think overall it was a good mix of various kinds of questions. So now the question for us is, what should we continue from next week onwards? So so I'll just suggest 2 or 3 possibilities, and I will allow you to vote that in your opinion what can we do. So what are the next plan for us? So one thing is that we can continue with theory topics, okay? Because we are still studying only geometry. We are not looked at other topics. So there is algebra, number theory, etc. So we have a lot of theory to cover. But when we are doing the theory, we'll go away from problem solving a little bit. So we'll focus more on the theory. We'll of course do problems on that topic, but we will not be contest problems. Okay. Then second is practice contest problems. Okay. So by contest problems, what I mean is that past RMO, IMO papers. Okay. So we have both of these possibilities available for us. And actually in that, like within that, there can be bifurcation, that you want me to focus on more on the simpler end of the spectrum, IOQM, RMO and INMO. So we have to choose that whether we want to do simpler questions or more difficult questions. So we have all of these things that we need to decide for the next lecture onwards. Okay, we also talked to Subodh sir and get his inputs that what based on what is going to be covered in the regular MPI lectures, I'll try to complement that with our practice sessions. But yeah, we have to decide accordingly that what we want to do in the next few months. Okay. Yeah, I think that's all I wanted to cover today. So I mean, there are few points which are kind of open-ended. Like if you want to analyze it more detail. By the way, this question 6, I did not talk about this. What about generalizing this? Like for 4x4, we got the answer as at least 7 points are to be colored. But what about 3x3, 5x5, 6x6? So that is open-ended. The first question also we have to generalize to n points. That is open-ended. Second question also, don't take the AB as the diameter, take it as arbitrary chord. Then what happens? So there are many things which are left unexplored. Even for question 4, I have given you an important separate problem to be done, which will allow you to solve an IMO problem. So you see, out of whatever problem solving we are doing, we are trying to generate more work for ourselves. That is not the end point of the RMO. That is a starting point for our next study topics. Okay. So whatever we do, we are going to keep this approach in mind. And so anything that you are studying on that in that way, you can keep sharing on the WhatsApp group. Okay, that's all for now. So yeah, like whatever plan gets finalized, we'll communicate on WhatsApp and we'll decide accordingly for from next lecture onwards. Okay, that's all from me. Anything you want to ask? Okay, then that's all. Thank you. Bye.